All right, this is the second part of the lenses video. For number 51, we're trying to figure out the properties of the image if you put something at point A. So if I put something at point A, let's see what it's going to look like. So if I go parallel here, I'm going to try to do this quick. So I'm going to bend towards the focal point here. And we say that anything that goes through the center does not bend. So they don't meet here, but they should meet somewhere else back here. Okay, that's a virtual image because for lenses, the image should be past the lens. Okay, the light should get through the lens, bend, and meet on the other side. So it's a virtual, it's going to be bigger, and it's going to be upright. Virtual, larger. So I think the answer is B. All right, let's look at 52. Which statement about images are correct? This is general, talking about mirrors, lenses, different types of mirrors, different types of lenses. A virtual image cannot be formed on a screen. That's true. Okay? And I'll show you that in class. We're going to do some demonstrations, and I'll show you that in class. A virtual image cannot be viewed by the unaided eye. We can see it. We can see images, virtual images. A virtual image cannot be photographed. Yeah, we can, because you can take a picture of yourself in the mirror, a plane mirror. A real image must be erect. Nope, real images are inverted. Mirrors always produce real images because they reflect light. That's not true. Convex mirrors don't, and plane mirrors don't, and even concave mirrors don't if you are between the focal point and the mirror. All right, so let's look at these ranking tasks. The first one says, okay, so if you are in water, there will be less bending, so which means the focal point is further out. So the distance for the image in case B has to be greater. Okay, and the reason for that is because the N for air is 1, for glass is 1.5. Here it's 1.33. For glass is about 1.5. So the difference here from 1 to 1.5 is larger than the difference between 1.33 and 1.5. So which means in case A, there will be more bending. In other words, the rays of light, as soon as they hit the lens, they're going to come together closer. Okay, so if they come here, the other ones may come together here. So the image for case B will be a greater distance from the lens. Okay. Now for mirrors don't rely on the bending of light. Okay, mirrors just rely on reflection, right? So so the image should be the same in both cases. Because again, because there is no bending of light. All right, let's look at 53. Which of the following terms describe lenses that are thinner at the center than at the edges? I talked about this in the first part of the video. Okay, so they are kind of like this. These are concave lenses, and they are diverging. So diverging, concave. A convex lens, which is this kind of lens, okay, has a focal length f. If the object is located at infinity, what we mean by that is it means like if the rays of light are coming parallel to the principal axis, okay? So they're coming from so far away that by the time they get to the principal axis, they look parallel. The image form is located at a distance from the lens of f. Okay, so anything that comes parallel to the principal axis will converge on the focal point. The convex lens, same kind, has a focal length f. If an object is placed at a distance of 2f, so that's basically placed at the center of the lens, okay? Not the center of the lens, but the center of curvature of the lens, let's put it that way. the image is going to be located at the center on the other side. Okay, so it's going to be at 2f. And this, for this stuff here, you have to go back to the drawings. Okay, 56. If an object is placed between a convex lens and its focal point, okay, so here's a convex lens, here's the focal point. If you put an object here, I just showed you earlier that you're going to end up with a larger, okay, upright and virtual image, love. Okay, so it's going to be virtual, upright, and it doesn't say anything about larger size, so it's just going to be A. Okay. Now let's look at 57. An object is placed in front of a thin lens, so it doesn't tell us what kind. Which statements are correct in describing the image formed by the lens? If the lens is convex, the image will never be virtual. That's not true. The image can be virtual for a convex lens if you put your object here. Okay? So that's out. If the image is real, then it is inverted. Well, all real images are inverted. If the image is real, then it's upright. That's not true. If the lens is concave, the image must be virtual. That's true. All concave lenses will give you a virtual image. If the lens is convex, the image must be real. Not true. Not between f and the lens. All right. I think 58 is a repeat. So we're going to look at this RT9. Okay. The figures. All right. The lenses are made of glass with an index of refraction of that. All lenses and mirrors have the same magnitude. Okay. Rank the the focal length of the mirrors and lenses when they are placed in water. Okay. So if they are placed in water, there will be less bending, okay, because now you're going to go from 1.33, these are made out of glass usually, 1.5, compared to between air and glass. So here there will be less bending, just like the one we did earlier, right, which means the focal distance here will be larger, and it will be the same for both of them. So it's A and B come first, okay. The focal distance for mirrors is not going to change because they don't rely on the bending of light, but they just rely on the reflection of light. So, and C and D will be unchanged and will come last. But for A and B, the convergence of light is going to come further out, okay, because the light is going to come parallel instead of bending like that, because the difference in the indexes of reflection is smaller between water and glass. It's not going to do this, but it's going to go and do that. Okay? All right. Okay. RT10. Object. All right, so this is a diverging lens. Based on the image of the object, find the two focal points. Okay. So basically, the way we're going to do this is that if we come parallel from here, now this is a diverging lens, which means the light does not come together, it spreads out. Now how does it spread out? Well, it spreads out as if it's coming from the focal point on this side, and it has to go by through the image here. So, but there is no light here, so we're going to just go like that, kind of. Okay? And if we extend this going through the tip of the image, this is the focal point. And you measure the same distance from the other side, and that's the other focal point. Okay? And I think I said the explanation verbally. Okay. RT11. An object is placed in front of a converging lens. An inverted image of the object is formed to the right of the lens. Okay. okay, so we're going to go parallel. Okay, this is a converging lens. Okay, so what we're going to do is we're going to go converge, and we're going to go through the tip of this image. Okay, and the focal point is right there. Okay, and the other one is going to be the same distance from the other side. Okay. Now, this one is a little tricky, so I'm going to label these two rays 1 and 2. Okay. It doesn't have to be a diverging lens, because even converging lenses, sometimes they diverge the light. Okay. Now, Brendan might be right. Okay. I don't think we can say this since an object inside. Yeah, so that's what I just said earlier. So this might be a converging lens. Okay. And for a converging lens, if you place your object between the focal point and the lens, you will see some light that's diverging. It seems to be coming from the focal point. Carlos also can be right, because this could be a ray of light that's going to go, when it comes out, it goes parallel, because maybe it originated from the focal point on the other side. Okay? Okay. Now let's look at some of these problems here. Let's look at 59. An object is placed 30 centimeters in front of a convex, so that's converging. So this is a positive 8. This is the DO. What is the image? So we're going to do that same famous formula. 1 over F equals 1 over DO plus 1 over DI. And we're going to do the magnification is HI over HO equals negative DI over DO. What is the image? Well, 1 over 8 equals 1 over 32 plus 1 over DI. And if you do the math correctly here, you should get 10.67. So 10 and 2/3 per centimeter. Okay. If the object is 3 centimeters high, that's HO. So we're going to do HI over HO equals negative DI over DO. So HI happens to be -1, I think. -1 centimeters. So the fact that it's negative here makes it real and flipped. Okay. Now the magnification is negative. I can do HI over HO actually. It's -1 over HO, which is 3. So the image is going to be 1/3 of the size of the object, and it's going to be flipped, which makes it real. All right, let's look at 60 here. Now 60 here, you have to be careful. They're talking about millimeters and centimeters, so they're mixing. So you have to decide whether to do millimeters or centimeters. All right, I think in my notes I did centimeters. Okay. So this is the height of the object.
Please rise for the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Good morning. Today is day D, and here are your morning announcements. Juniors who are approved for parking, please check your emails for an important announcement. You may not park in the lot on Thursday, May 31st. Please make alternate plans. Here's Dr. Sabatini.
Good morning. A reminder, 11th graders, NJSLA science test be administered tomorrow, Wednesday, and also Thursday morning. 11th graders are asked to report regular time to assign rooms, report to school no later than 7:30 a.m. as usual. 9th, 10th, and 12th graders will report on a delayed schedule. Report no later than 9:15 a.m. for a modified delayed opening schedule that will commence at 9:30 a.m. on Wednesday and Thursday this week. Congratulations to the Kinnesis Modern Dance Club on a great show last week. And also congrats to our marching band on a performance in the Memorial Day Parade in Harrington Park yesterday. Congratulations to the 100+ students who participated in the Teen Arts Festival. Very proud of all of our students who participated. Congratulations to our boys track team and coaches, Group 3 North 1 state sectional champs. Congrats to our girls team, had a strong showing, finished in 3rd place. Thank you.
All right, sorry about that. I'm not going to edit this video, by the way. Okay. So we're going to use the lens formula here, or the mirror formula. So we're trying to find the location of the image. So we're going to do 1 over f is 1 over do plus 1 over di. I should just keep this here. Okay. Okay. And I gave you the proofs to these formulas in another video. All right. So di is positive, which means your image is past the lens, because that's what it's supposed to be. Okay, now we're going to find the height. Hi over ho, which is 0.225, equals negative di over do. And your image will be negative 0.41 centimeters. Okay, so which means it's inverted and it's real. Okay, which means that's why it's on the other side. Okay, let's look at 61. An object 5 centimeters high, so that's HO, is 3 centimeters in front of a converging lens, so that's a convex lens. And the focal length is positive, so just pay attention to stuff like that. Where is the image? All right, so we're going to do 1 over 4 equals 1 over 3 plus 1 over di. So di is going to be negative 12. Okay. And it makes sense because your object is between the focal point and the lens. Okay, so your image is going to be on the same side as the object, which doesn't make sense. It's supposed to be on the other side. So if it happens to be in kind of like the wrong place, that's a virtual image. Okay, trying to find the magnification, it's negative di over do. So it's a positive 4. So it's larger, and that's expected, and it's virtual. Okay. And 62. An object is 30 centimeters to the left of a convex lens. So the f is positive 5, the do is 30. Now we're trying to find the image. 1 over 5 is 1 over 30 plus 1 over di. So di is positive 6 centimeters. So that makes it a real image. And we know that it's going to be real because we are to the left of the focal point, right? So the image would be past the lens. Okay. And the height should be, okay, so this is HO. So the height should be negative because it's going to be flipped. So HI over HO equals negative DI over DO. So HI is going to be negative 0.3 centimeters. Okay, so we knew it was going to be flipped and it was going to be on the other side. All right, and it's going to be small because you're way to the left of the focal point, past the center of the curvature. Okay, let's look at 63. Okay, an object is placed to the left of a 25 millimeter convex lens, so that's a positive. So that its image is the same size as the object. Place to the left. Okay, so if it's to the left, this is going to be flipped. Okay, so di over do, or negative. Okay, actually I can do it with hi. I can say hi over ho. Since we are to the left of the, to the left of the focal point, so this is going to be a flipped image, so this is going to be negative. Okay, so this is going to be -1. And that's going to be negative di over do. Yep. Okay, so now it's asking us to find what is the image, what are the image and the object locations. So we can start with one of them. So I can say 1 over 25 equals, now here we can see that di is equal to do. Yeah. Okay, so it's going to be 1 over do plus 1 over do. So this is going to be 1 over 25 equals 2 over do. So do looks like it's 50 millimeters. Okay, and that should be expected because the image and the object are the same size, and they're going to be flipped. So which means the object has to be at the center of curvature of this lens, and di will be also 50 millimeters from the other side. A lens is used to create an inverted image twice as large as the object. So hi over ho is -2 because it's flipped. Okay. So the object has a height of 2 centimeters. When the object is 7 centimeters from the lens, so that's do, what focal length lens is used? Okay, so I think we can say that this is going to be equal to negative di over do. Okay, which means that 2 is equal to di over 7. So di is 14. So we can do 1 over f equals 1 over 7 plus 1 over 14. This becomes 2 over 14, 14 over 3. So the focal distance is 14 over 3, which is 4.67 centimeters, and it's positive. Okay. Okay. All right. An object, 65. An object 4 centimeters to the left of a convex lens. So this is do, which has a focal length of 6 centimeters. So that's a positive because it's a convex lens. Find the image location. So this is going to be 1 over 6 is equal to 1 over 4 plus 1 over di. So di is going to be 65, -12. Centimeters, and that's expected because your object is stuck between the focal point and the lens, the convex lens. So trying to find the height, hi over ho equals negative di over do. So hi looks like it's 6 centimeters, and it's positive, which makes it upright, which makes it virtual. All right, let's look at some of these multiple choice questions. A cell phone is placed 40 centimeters in front of a converging lens, so that's a convex lens, with a focal length of magnitude 20 centimeters. So that's a positive 20. How far is the image of this phone from the lens? Well, hold on. So we can do this conceptually. We don't have to do any math. So if you are 40 centimeters in front of the lens and the focal distance is 20, it means you are at the center of curvature. So your image will be at the 40 centimeter mark on the other side. Okay? We can do the math here to show that it works too. So 1 over 20 equals 1 over 40 plus 1 over di, and you can see that it should end up with 40 centimeters. A wrench is placed at 30 centimeters in front of a diverging lens, so which means the focal distance is negative. So this is DL. What is the magnification? So I think we can eliminate some of this stuff here. If it's a virtual image, if it's a virtual image, anything that's negative for magnification will be out. And I think for a diverging lens, we end up with a smaller image. So the magnification has to be less than 1. So it comes down to either A or C. So let's do the math here. So I think if we find di, we can do the magnification. So 1 over negative 10 equals 1 over 30 plus 1 over di. Di will be negative 7.5 centimeters. Now if you do the magnification, you do negative di over do. Okay, and that looks like it's about 1/4. Okay, so the answer is A. How far from a lens having a focal length of positive 50 millimeters, so that's a convex lens, must the object be placed so it is to form a virtual image, so it's an upright image that is 3 times the size of the object. So HI over HO equals positive 3, okay, which is also equal to negative DI over DO. Okay. Okay, so I think DI here is negative 3 DO. All right, so let's do the math. So we're going to do 1 over 5. Well, I can do everything, and since the answers are in millimeters, I'll leave everything in millimeters. 1 over 50 equals 1 over DO plus 1 over DI. And I'll just throw a negative here. So I can make this a 3, make this a 3. 1 over 50 equals 2 over 3 DO. So that looks like it's going to be 33 1/3. So the answer should be A. Okay. A 4 centimeter tall object is placed, so this is HO, is placed 50 centimeters from a diverging lens. So the focal length is negative. So they give you the magnitude of it. So this is your distance for the object. What is the nature and location of this image? So since it's a diverging lens, it will give us an upright, virtual, and smaller image. So let's say anything that says real has to go. So A and E are gone. So it's a virtual image, and it has to be on the same side as the object. Okay, because it's in the wrong place, kind of. Okay, so B and C are gone. So you're left with D. You don't have to do any math for this one, but if you want to do the math, let's do it. So we can do 1 over negative 25 equals 1 over 50 plus 1 over DI. And we get a DI equal to negative 16 and 2/3 centimeters. Okay. And if you want to find the height of it, you're going to do HI over HO, which is 4, equals negative DI over DO, which is 50. So this looks like it's a third, so that should be about 4/3. So it's 1.3 centimeters tall. But I think we can do this just conceptually. We don't have to do any numbers. All right, let's look at number 70. Now 70, I'm going to do the drawing quickly, but I'll take the time to do the math. Okay, so the axis of this lens, the principal axis, is kind of like there. Okay, maybe a little lower than that. Let me try. So this is about 59. So it's about here, somewhere around there. Okay. So now if we want to make the, okay. You know what, I'm not going to do it to scale. So the object is at the center of curvature of this lens, because the focal distance is 15 and this is 30 centimeters away. So I should expect my image to be 30 centimeters to the right of this first lens. Okay, so basically the image is going to be is going to converge twice. Okay, so I can go parallel here. Okay, and find the focal point here, which is about at the 15 mark. So maybe here, and do something like that. Okay, and also I can go through the center and not bend. Okay, so that's the image of the tip of the flame. Now we have to do the same thing for the bottom of the what do you call it? The candle. So we do the same thing. Go up this way, and anything that goes through the center does not bend. Okay, so we should see our candle here, upside down, same size as here. Okay, then now you are 20 centimeters from the other lens, which happens to be twice the focal distance, which means you are at the center of curvature of this other lens. So now you should end up with an image that is 20 centimeters from this side, and it's flipped again. Okay, so it's going to look upright basically. Now upright does not make it virtual in this case, because you have to deal with two lenses. So what happens is that the first lens flipped it, but it kept it real. The second lens flipped it back, but it also kept it real, because the images in both cases are happening where we expect them to happen. So just be careful. Just because it's upright does not mean it's virtual. That's true for one lens. All right. So now let's do some of the math. So now what I'm going to do is that I'm going to try to find the location of the image after the light passing through the first lens. Okay, and that's going to become the object for the second lens. Okay. So let's see how we can do this. So I'm going to do 1 over 15 equals 1 over 30 plus 1 over di. And my di will be, it's going to be 30 centimeters positive, which means that it's formed in the right place. Now I subtract 30 from 50 to figure out how far is this image of the candle from the second lens. So it's going to be 1 over 10 equals 1 over a new di, so I guess I can call di1 and di2, plus 1 over 20. Okay, so this di2 is going to be equal to 20 centimeters. Now, to find the magnification of multiple lenses, all you have to do, and maybe I'll show you the proof to this in class, is you take the magnification for each and multiply them together. If you have 3 of them, you just multiply all 3. So it's going to be negative di over do. That's the magnification of the first one. Now we do the magnification of the second one. It's going to be negative di over do. And that should be a positive 1. And that's why it looked upright at the end, but it was still real. Okay. And the fact that the magnification is positive 1, it means that it's same size as what you started with. All right, let's finish with the 71. Okay. 2 converging lenses, so you have one here, another one here. This one has a focal distance of 10 centimeters, positive 10. This one is positive 15 centimeters. They are 40 centimeters apart. Okay. An object is placed 60 centimeters in front of the first lens, so it's here. So this distance here is 60 centimeters. Find the position of the final image. Okay. So I'm going to do 1 over 10 equals 1 over do plus 1 over di for the first lens. This is lens 1, this is lens 2. So di 1 is equal to 15 centimeters. Is it? I think I changed the numbers here, so okay. I think I changed the numbers to f2 to be 8, and they are separated by 20 centimeters, and this one is placed 30 centimeters from the first lens. Yeah, I think that's what I did. Okay, so this is 30. This here is positive 8. Not sure why I did that, but 20. So let's fix this. 30, so di1 is going to be 15 centimeters. And it's positive, which means that it's real. Okay. Yeah, I think I made some changes here. All right, so I'm just going to continue with this. So now so we're 5 centimeters. I think I kept this as 20. Yeah, okay. So now we're 5 centimeters from this lens here. So now I'm going to do 1 over 8 equals 1 over 5 plus 1 over di2. So di2 is going to be equal to negative 13.33 centimeters. Okay. Okay. So what is the image going to be located? Well, it's 30, okay, plus 20 minus 13.33. So it's going to be 36.67 from the initial position. So it's 36.67 centimeters from the very first location. right? So to find the magnification, I just have to find the magnification of each. So negative di over do, which was 30, times negative 13.33 over do, which was 5. So this should be negative 1.33. Okay, and no units. All right, and that should do it.